Well, the idea of this lecture is very similar to the previous lecture in a sense that they both use span-based approach for semantic parsing. So I want to explain this article, Span-based semantic parsing for compositional generalization, based on or inspired by these articles from 2017, 2019, and 2011. So this is the span-based SP. So its example is a span tree, and nodes are annotated with categories in bold. So a node with category join here, for example, over any span over I and J, is annotated with the subprogram ZIG. But if you want to put this into a little distant supervision instead of full supervision, because sometimes we don't have access to the full tree, so you can say that this is the program that they may give you, but they don't tell you the details. So this is a kind of distant supervision. But most of the time, you have access to the tree in the goal tree. But it's very expensive. But in this problem, it's easy to construct that kind of tree. And we assume in this paper that we have goal trees. So it extends the Passbook 2019, as I said, it is inspired from that. So we train program without access to the goal trees, treating trees as latent variable. So we don't have access to the goal tree, but we have access to the last one with the root of that, the root of that, which is the parent of all, the highest parent, which is the root. And this Z is the logical form in a different paper, but another kind of supervision is that distant supervision is that, for example, you have access to the answer, you have the world and you have the answer, and you backpropagate the gradient and errors in order to resolve what is logical form, which is hidden and latent. But latent here, it means logical, the program here. And so the span-based approach, we predict for every span in input category, which is either a constant from the underlying knowledge base, a composition category, or a null category. So given the category predictions for all spans, we can construct a tree over the input utterance and deterministically compute the output program. For example, in this picture, you see that the category for the tree node covering the span New York borders, this span, is the composition category join, this one, indicating the composition of predicate next to one with the entity state ID, New York, with this constant New York. And so the contributions are like this. First, categories are predicted for each span independently. You know, in the last lecture, we assumed that we are using the max margin, and we assumed that you can use CKY in each step of the training. But here, we are not using CKY at the training, but still we are using it at the inference. So categories are predicted for it. Like previous lecture, we still use the categories, and we are not using that CKY at the training. So here is because it inspires from the previous paper, so it's very similar. But the reason that the contribution is that we enhance the applicability of span-based semantic parsers in both supervision and expressivity. We do not use gold, so the idea is that we do not use gold trees as supervision, only programs we know with no explicit decomposition. As I said in the first slide, we are just given the last one, the tree, the root. So to train with the latent trees, we use hard expectation maximization approach, where we search for the best tree under the current model corresponding to the goal and update the model based on this tree. Second, some goal trees are non-projective. You see sometimes happen that you get something that, for example, this most is not in the middle of this word, and so it's not contiguous, and thus we have some problem, but we can add to the grammar, no problem. So the problem setup is that we have a span tree very similar to constituency trees. Everything like previous lecture. A span tree can be viewed as a mapping from every span to a single category. But here categories are different. Categories are like join and those very simple things, where categories describe how the meaning of a node is derived from the meaning of its children. A category is one of the following. So it's a set of domain-specific categories representing the domain constant, including entities and predicates such as capital, state, location to next to one. And also join. Join could be a category. Join a category for a node. And also null. When it is null, it means that a category for does not affect the meaning of the other. For example, in the figure one, the nodes when we say what is the and the question mark are tagged by null because they do not correspond really to the constituents. So we define the span-based semantic as follows. So we have a training set, you have X, and X is your input utterance, Z is the corresponding program that we want to discover because it's a latent variable. So the computing program for span trees is as follows. For example, given a mapping from span to category specified a span tree, we use the function program to find a program for T. So you know what I'm talking about. So this is the span-based semantic parser in which, so our parser is based on a model, this model parameterized by theta that provides for every span T, I, and J, for every span, a distribution over categories. For example, what is the probability? Let me show you an example. So it's for every span it's a distribution over, like previous lecture. We had those nodes, those categories. Due to above independence assumption, because we assume that they can be independent, of course they have some correlations, positive correlations, but we assume in this paper that they don't have any correlation. Everything is independent. That's why you can multiply them and create a beautiful, easy likelihood. And because the log of multiplication is just sum of them, we can just create this, and so the sum is over all spans, not only over constituents. So now we want to model this p theta, and what we do is here. So we just like the standard way, we define a real value score of a very span, and having category C. What is the score for the span I and J to have category C? So you see we've concatenated, then multiply by vector by weight, and then we have ReLU nonlinearity in our neural network, and then we have weight, and we are just learning these weights, W1 and W2, and so on. So this is the index. This one is the index of the category, because we are looking at it like previous lecture. We were looking at it as a classification problem. So for each category, there is a probability. And because we have used a softmax of S, so it becomes a probability. And now use cross entropy over average span over all spans. And so CKY-based inference. As I said, like previous lecture, we don't use CKY at the training, and this is beautiful. It becomes fast, very fast, because we are just using CKY-based inference at the inference time. So while we assume span independence at training time, at test time we must output a valid span tree. We now describe an approximate k-best CKY algorithm that searches for the k most probable trees. So you're all familiar with CKY, I just skip it. So the CKY, the grammar that we want to say is very simple. For example, we say S is composed of join and join, or S is composed of null and join. And another one is join is composed of join and join, or join and null. So the likelihood, like before, this comes out of, because the log of exponential is itself, but this, because of this summation, we cannot remove it, so this becomes simplified. So we shift scoring function for each span such that the score of phi category is 0. So because softmax is shift invariant, we can replace S and S. That's the technicality, so we skip it. What is important here is the tree score, like any other article that I've explained recently. We just add these score of constituents. I is less than j. For any span from I to j, we add the score of that. So say that the score of xi and j having category t of I and j. If you sum them, then we get the score of a tree. And this score can be maximized using CKY algorithm. Once you get these little scores for these constituents, then you are done. And you know CKY inference algorithm is so easy. It's dynamic programming. It goes back to 1945, maybe 1960. So it's very old because it's very easy. So our non-terminals are just S and join. And this is our set of terminals. You know, R is a set of rules. We have 4 rules. 1, 2, 3, 4. S is just the start symbol. Nothing important. And when you move, we get that the grammar can generate trees that are not semantically varied. For example, we could generate the program capital of place ID of Mount McLean, which is semantically vectors. And we use a domain-specific type system and assign a score of -infinity to every tree that yields a semantically invalid program. And another thing that we should note is that once inference is done, we retrieve just the top k trees from this pi. So now we want to talk about training without the gold trees. So we remove the assumption that we have access to gold trees at training time, where we only have access to the gold program Z without this decomposition. So it's just the Z at the top, at the root level. So we don't have this decomposition. We don't have access to these. We don't know the categories of these nodes. We just know the final program when it is the after all compositions. So our goal, because the probability of your program given X, because there are many trees, that can create, you can create some other trees. This is another tree. So because there are many trees that have the root Z, here the root Z, there are many trees, so we sum over them. Just like PCFG, probabilistic context-free grammar, in my playlist for probabilistic context-free grammar, we had many things. So we had and the CKY could tell us what is the maximum probability. But here we are just writing the probability of your latent variable given your utterance. And this is a weakly supervised setting where the correct span tree is a discrete latent variable. We don't know these. They are very latent. We only access to Z. And so this is the training without the gold trees. And this is just a simple technicality, exact match features. And sometimes we have, many times, when we have some kind of superlative, for example, most in your sentence, unfortunately, it's not projective. So it's non-projective because it's non-contiguous and non-adjacent. So state has the most people. You say it's not. We cannot use projective. So that's why we add, no problem. We add the ternary grammar rules, join. So we can resolve this issue, no problem. So consider the top case scores, and then we can now resolve the non-projective tree. So this is the final thing that we have discovered. It's a very beautiful approach. We are not even using those combinatory category grammar, CCG, that I will explain in a different playlist, because sometimes people use CCG. CCG is originated from Eindhoven University, Edinburgh, or Eindhoven. No, Edinburgh in Scotland. And CCG, I will explain CCG in my playlist on probabilistic combinatory category grammar. But here you see that we didn't use this CCG. We are just using some categories, simple categories like the previous one. Of course, if we compare that, we can say, okay, this is the kind of type of that, and this is that logical rule. But the aim of CCG is something else. In CCG, we are not creating the score and measuring the score and like that, because we already know that, okay, I will explain about CCG in a different lecture. And this is a span-based SP. So this is for lexicon non-projective. You see the accuracies is quite high. It's very nice. Except this one, 68, which is for this dataset GeoQuery. And so you see the scores of all of them are almost higher than 80%, which is 30% above chance